You decide.
Okay. Okay. We are recording. Okay. A good evening to everyone if you're in Europe, and good afternoon if you're joining us from USA and anywhere else in the world. On behalf of Young Professional Society YPS and STEM Matters, I would like to welcome you to one of our series of webinars which we've been holding on a weekly basis. And we're very, very pleased to have with us a very important, a world-renowned speaker, Professor Werner BLAU, who will be speaking to us about where a degree in physics can lead you. Astronaut, comedian, German chancellor, nanoscientist, or radiographer. So these are some of the things that Professor Werner BLAU will be speaking about. And these webinars have been brought to you by YPS, Young Professional Society, in collaboration with STEM Matters, who are based in the USA. And Young Professional Society has been set up to help and support youngsters with personal and professional development. So the aim is to try to support youngsters and try to transform lives so that they become more successful professionals in their working lives. And we focus on three areas. Number one, innovation. Number two, communication. And number three, leadership. And these webinars that we bring to you is an effort to try to help youngsters and learn from senior people, professionals who are successful in their own fields. And these webinars have been brought to you in collaboration with STEM Matters. And STEM Matters were based in the United States, and their vision is to enable students to innovate, invent, and deliver quality solutions to contemporary challenges. Before we move on with our webinar and to our speaker, I just want to put this slide up so that those people, if you want to know more about YPS and STEM Matters, there's websites that we have. We're also active on Facebook, and you can see us, and we have a YouTube channel as well. So all these webinars and our programs that we do, you can find them on our YouTube channels, and there's an email address there as well. And those, if you want to, if you're interested in becoming a member of the Young Professional Society, you can find all that information out on our website. So please do take a note of that. Now I want to move on to our special guest speaker, Professor Werner BLAU. I just want to give a brief introduction, and I'm sure Professor BLAU will introduce himself as well in his presentation. But Professor Werner BLAU came to Trinity College Dublin in Ireland in 1983 as a research fellow, working with Professor Bradley, who's a FRS, after completing his PhD in Germany. And since 2003, Professor BLAU holds a personal chair of physics of advanced materials, and from 1992 to 2007, he was a research director of the Materials Ireland Polymer Research Centre at Trinity College Dublin Physics Department, a research centre which worked closely with Indigenous Irish plastics industries for all sectors, including electronics, medical devices, and materials processing. Professor Werner BLAU has published over 340 peer-reviewed papers and is a co-author about 13 patents. He has supervised over 80 postgraduate student and postdoctoral research fellows. He's a fellow of the Institute of Physics, fellow of the Institute of Nanotechnology, and he's one of the Irish pioneers of nanotechnology. He's an internationally well-known and highly cited for his original work in interdisciplinary molecular and polymer nanoscience. His research group, was one of the first in the world to adopt an interdisciplinary approach, including chemists, physicists, material scientists, optical and electronic engineers, and polymer technologies. Carbon nanotube related IP generated by the group has been successfully licensed by Trinity College Dublin internationally. So I think without further ado, I will pass over to Professor Werner BLAU, who can now share his screen. And we do have Professor Waqar Ahmed from Lincoln University, who will be co-hosting this. And Professor Werner BLAU.
Okay. So from my end, good evening, everybody. It's getting dark out here, and I'm giving this talk. Actually, that's quite some interesting aspect from the utmost end of Europe. I'm sitting in North Mayo, which is sort of there's only water out here until you get to Canada and America. So just on the Atlantic edge. So it's quite amazing that this is a possibility. Now, when NASA asked me to talk about something from a career, I thought I'll just give you a little bit of an impression how exciting physics as a career choice can be and where it can lead you. So to start with this, Nazar asked me to just introduce myself. And as you will have seen from his introduction, you know, life in science is moving quite fast insofar as publication goes, because when he said 340, that was probably about 5 years ago. It's now about 500. So I think he's introduced most of these. I was born in Regensburg, which is a town near Munich. I have a photo later on because we have collaboration with there. And and I will in the next slide give you my path into a physics degree. But when I then finished my doctorate, actually I should say I didn't have that. After my undergraduate degree, or whatever a diploma it is in Germany, I went to join Siemens research labs for 1 year. And the interesting aspect on this, we were working on superconducting magnets. And there's two aspects to this which have a really interesting up-to-date component, which is very interesting because it tells you how long it takes to develop something, even in an industrial context, from a concept into a daily life. And there's 2 points where you use these magnets. One is we were working on levitation, magnetic levitation trains. And if I go to Shanghai now, there is a Siemens train on the same concept, not superconducting, but a magnetic levitation train. So it's actually reality. And the other one is we were working on magnets for a medical project, which we weren't told what it was. And just about 2-3 weeks ago, I had to do an MRI scan of my hip because I heard something. And it was MRI, magnetic resonance imaging, which was in its original times at around 1980 or something, when the Siemens was developing that. And in fact, Siemens was the machine I was actually lying in to see that. So it's quite interesting. So why did I do a doctorate? Simply because at the time, at least, it was clear, and probably is still somehow the case, that in order to actually get to work independently and to develop your own group and so on, you had to get the doctorate, because the doctorate shows that you can work independently. And so I went back and started the doctorate in laser physics. And when I finished in '83, the normal way, we had actually a 3-year-old boy, uh, and we were saying, my wife had just finished her psychology degree, and we were saying, if we don't go abroad now, we will never, because once the child gets into school, you're fixed. And so we looked around, and the normal way to go would have been to go to the United States. And in fact, I did apply to various places there and got various offers. But what came out of this, if you remember 1983, that's way before your time, I would guess. That was the time when a president called Ronald Reagan was president, and he was very heavily into what they call Star Wars, or the Strategic Defense Initiative. And some of that was to use lasers to shoot down missiles. And all what I had in job offers was somehow related to this kind of military application. And I said to myself, I didn't have to join the military by conscription in Germany, so I didn't want to join it anywhere else either. So we were looking to Ireland, and in Ireland, as Nazar said, there was a really well-known laser physicist called Dan Bradley, who had actually introduced the lasers to the British Isles and started initially a laser department in Queen's University in Belfast, which was world-renowned at the time, and then came down to work in Dublin. And he was looking for somebody, and I had seen his name. So with a little boy on my arm here, I took a phone call and I got an offer to come over and do an interview. And anything else after that, from my point of view, is history. We moved over, and then I just went through the academic ladder there, where I'm rapidly approaching, as you can see from my face and the development, rapidly approaching my retirement at this stage. As is normal in academia, there is, you get sort of other positions offered where you can visit occasionally. I've visited many places for times in the USA, in China, in Japan, in Germany, of course, being German there. And I have various honorary professorships in China, mainly at the moment active there. All the industry and publication was already mentioned by NASA. Now, just to say, Trinity College was founded by Queen Elizabeth I, number one, in 1592. So it's a historical college on the Oxford-Cambridge model there, but in the city of Dublin, in the center. It's the University of Dublin, and Trinity College is the only college of the University of Dublin. And our physics department was built around 1905, and is in the Fitzgerald Library, named after John Francis Fitzgerald, who, in fact, amongst many famous things in relativity theory, also was the first guy to buy a glider from Otto Lilienthal in Berlin and make a flight on the British Isles there from what is now the pub on campus there called the PAV, the Pavilion Bar. If we do research, I just want to show this here. we never work alone in physics. It's always done in teams, and people work together in teams. And your education is also an education if you do it in physics in teamwork. So teamwork is important. And as you go through the years, groups grow, as you can see, and shrink. And there's various photos of members of the group in various stages of my career there. And one thing I will say later on, as you can see, we grow older and your productive time, and I'll take the Einstein example later on, is when you're in your 30s and 40s. So you don't look like this old guy you see here. You look more like the historical photo there. There's also a photo of getting the nanosmat, famous nanosmat prize, which is where NASA is the director of the Nanosmat Society, I think the oldest and most active nanomaterials and nanotechnology society on this globe, from Andre Geim, who is the Nobel laureate in Manchester, who developed the graphene. Now, at the very bottom right, you can see what I do on Sundays. Namely, I didn't just study physics, I also studied music, and at some stage decided that making a career, and I finished both, but making a career in music is very, very hard, because all you can do is essentially either play the organ like I do here, and make a career in something like education and religious services or so, or you become a soloist, and then it becomes almost impossible to compete on the international scale. And in fact, the creativity you have in physics is just as good, if not in physics. Now, I just want to show you how did I get into physics. Now, this is never a direct path. It's in fact many angles, I think, which come together, many aspects which come together. And they go back essentially to the early teenage years. I had a half sister who unfortunately died in March there, or April this year. And for Christmas and for my birthdays, at some stage around the age of 12, they discovered that I loved these experimentation sets. In Germany, they were called Cosmos. They're Cosmos sets, and there was one in electricity. I remember that was my first at Christmas, called Electroman, and there's one in optics called Opticus. There was also one in chemistry and one in some kind of biology and so on. But mainly the physics ones were the ones which I really loved. So the electricity and the optics one were my absolute favorite there. And when they discovered, of course, that I loved them, almost every Christmas, almost every birthday, I got something to do with this. And then also books which tell you how to do experiments. And at some stage, I think it was in Germany, you started and still start counting years from the first year you start. I think something year 8, which would have been the 4th year in secondary school, we started having physics, and we got the physics books at the end of the previous academic year, or all the school books, I should say. And when I saw the physics books, I started reading it. And I was absolutely fascinated with it. And in fact, the whole book was due to cover 4 or 5 years of physics, and I read it over the summer, and I loved it. And when the teachers, some of them were really supportive, supportive noticed the love of physics, then they would, for instance, allow me to set up experiments together with them in the afternoon for the next day, for the next course. And important is you have to essentially find good books, and they have to actually click with you, and you have to have people who are supportive. Another angle which brought me very close to physics was that at some stage there were sort of competitions on maths and physics in the school, and at some stage I won a Bavarian competition to visit the German Museum of Technology. This is, in fact, if you ever come to Munich, this is an absolutely massive, absolutely fascinating museum, which is full of technology and technological development. And in physics, chemistry, biology, you can do your own experiments, and you can do hands-on on this. And what fascinated me most at the beginning was here electricity again. They have a high voltage demonstration where they show you 1 million volt arcs and Faraday cages and all that. And this is really fascinating stuff. And what I also loved at the time was, for instance, they have the original experiment which Otto Hahn and Strassmann did when they did the first experiment on nuclear fission. So splitting uranium to create energy, and the beginning of nuclear energy. And I found this very exciting. So I started learning about nuclear energy, which of course at the time was projected extremely positively and is still extremely important, for instance, when you think about it in terms of nuclear medicine to can destroy and cure cancer, or as energy sources for these satellites which go out hundreds of millions of kilometers away from the sun. And in fact, radioactivity produces heat, and heat can be converted to electricity. Those satellites are powered, and this is going to be really an important topic if we ever do interstellar travel, an important energy topic there as well. On the basis, then I started doing my own experiments, and in fact, what came out was a guy who looked somehow like this. I remember several times having explosions in the room, and my mom throwing me out and throwing all my experimental setups into the bin, where I dragged it out again. But the actually the spark of this was set there. And then I did a computer science, informatics it was called, project in a young scientists competition as well, and won a Bavarian prize, which was I think 300 Deutschmarks, which is a huge amount of money for a teenager. So all these tracks were laid towards physics for me in the teenage years. And the important is that you pick up what you love to do, and when you love doing it, you do it best. I think that is one of the important aspects in your career planning angles as well. Now, let me go ahead and just tell a little bit about what do you do when you're going into physics. Now, here's a guy whom you probably have seen before, called Albert Einstein, and he tells you something. He should actually move, but he doesn't move. So one of the things he said is, the world stands before us like a great riddle. So we want to actually see and understand how the world around us works. That's what we would have in previous years called natural philosophy, understanding how nature works. And the physicist's goal is to solve these riddles posed by nature. And it can go, as Einstein says, and as I say, from the birth of the universe, the Big Bang theory, to what he called the atomic conundrum. The atomic conundrum in Einstein's times, which was the 1920s, 30s, where he was the guy, this is the interesting one, he was the guy who proposed much of it. At the same time, he didn't believe it. But he was right in the end and proven right as such. And the atomic conundrum is the fact that when I take something like this spoon and I move it, I can see exactly where the spoon goes. It goes from here to here. And if you go to an atomic scale, it could be either here or there. Quantum mechanics says that there's a probability, and you have a probability to find it here or there. And that's what Einstein called, does God play dice, as a question he posed that. Does nature in fact work on probability? And in fact, at the atomic levels, yes, it does, and we get there. So physicists, he says, are like detectives trying to solve a mystery. So that's, in fact, you look at your mystery, whatever mystery you want to solve. If it's the beginning of the universe, if it's the question if the universe is expanding or contracting or infinite or finite, if there's something, how is our matter made? Is there something which is smaller than is in the atomic nucleus? Can we split a nucleus into smaller particles, into quarks, and so on? So there is a whole range of different questions. You pick the question, and that's the nice thing, and which you want to answer. It can be very fundamental, and it can be very applied. Personally, I've always, that probably comes through my interaction with industry at the beginning, being really interested in practical questions. And one practical question where nanotechnology comes in is, can I make electronic devices smaller and smaller and smaller? And what happens when I'm down to a single molecule? Can I make a transistor which is a single molecule? And the answer is yes, but it's extremely difficult. And yes, it's even more difficult to actually verify that you've done that. So we're detectives, and it's detective work to solve these mysteries. So there is a whole range, as I mentioned, of different aspects related to physics, and you just pick whatever you want to do, and you find something to solve there. Let it be force or energy. Energy and renewable energy is a very, very important upcoming topic. Quantum technology, or whatever, electricity, electronics, molecular electronics. You have a whole range of possible subjects. So when you look at studying this, you have essentially a number of central theories here, which I just go through there. There's the classical mechanics. Again, this should move, but it doesn't there. And the classical mechanics is essentially large objects which move from one place to the other. That, of course, in development can be used and applied, and physics and science basically puts the basis, the scientific basis, onto something which then technology and engineering brings to a stage where the general public and the society can use it. So this is a very, very close interaction as well. And if you're much more into having something developed into for society, you probably tend more to engineering. If you want to look at the more fundamental aspects, you look at science. But the link between that and we always have collaborations, and we always have actually students from either way working in the other direction. You can pick and choose, and you know, I mentioned the magnetic levitation train, for instance, or classical mechanics, going back to Kepler in the 15th century, how the planets move and how the Earth rotates, or making, say, devices to let us move better. So medical implants, for instance, or something like that. That's essentially the classical mechanics is the origins for all this. Electromagnetism is the next lot. Yeah, I don't need to basically explain too much to that because you're all using it right now when you're looking at this. You know that opposite charges attract, same charges repel. That's basically the physics law. You apply this to make devices, and you can make essentially transistors and electronic devices, put them together, and you have, for instance, a mobile phone, or you use it to make radio waves, and you can either use radio waves to look at the origin of our universe, for instance, is one way, or at communications between places. And that's, of course, the basis, very much the basis for telecommunications in that case. And within electromagnetism, of course, light is electromagnetic waves, optics and light and lasers falls under this heading there, onto this central theory as well. Thermodynamics is another one. This is basically classical mechanics when you have many, many small particles. There, it's called statistical mechanics because you can make averages only. And that's, of course, important for energy. And for instance, used to model and understand how a rocket propels itself, as well as used in making fridges, for instance, and heaters and heat pumps, and you name it, as you can imagine. So this is essentially to do with heat and temperature, where you control many, many atoms on average. If you look at the individual atom, as this lady should theoretically do here with her magnifying glass, then you come to quantum mechanics. This is the question on how does matter behave on the atomic and subatomic scale. You can only do probability statements at some stage there. But that is really, really the big breakthrough of the 20th century there. And the other fundamental theory, which I just want to mention, is, of course, the theory of relativity. That's something which is sometimes very counter-intuitive. This should be, for instance, a clock which goes backwards, or a rocket which moves fast. In that case, important, of course, Einstein came up with the theory around 1905, and with the special relativity theory, and it's so important for our understanding of the universe now, and possibly the way to do interstellar travel if you ever get there, and the future of our technologies rely very strongly on something like that. So you split it, and you can essentially look at a whole range of major fields based on the combination of all these central theories. One is condensed matter physics, is basically the physics of all the tangible materials. If it's a crystal, if it's a piece of glass, if it's a piece of plastic, that's condensed matter physics. Then atomic, molecular, and optical physics, which is essentially the interaction of electromagnetism with atoms. Particle physics, for instance, how is the nucleus of an atom made of? And this is the very large accelerators like you have in CERN in Geneva, and astrophysics, very interesting questions on cosmology. Where does the universe come from? How, are we alone living on a planet which is habitable? There's a whole field of several thousand of exoplanets which have been discovered in the last 20 or so years. So there's a whole excitement. And I hope what you get out of this is that there is a lot of, there is never, in research and in anything you want to learn, there's never an end. An end is never in sight. There's always something further to find out. So there's always the excitement to find something more. And what recently, or not recently, but in the last sort of few decades also came out is that physics is very important in various aspects in biology and medicine. I mentioned the magnetic resonance imaging, biophysics, of course, the physics, for instance, of sensing is very, very important. And as you can appreciate in the current situation, sensing some virus is an important aspect. So physicists have their role to play in that. Geophysics, understanding what happens with our natural resources, and of course in this context global warming and climate physics and climate change comes in as a very important field. And for instance, where you would not expect it is econophysics. You can, for instance, model the economy on statistical mechanics terms, and you can predict things like stock market developments from using physical models in that case. So there's also these developing interdisciplinary fields. So it's not a one-way track, it's actually a track which can branch out in many, many directions. Now, one thing I want to say here with my little Einstein who didn't move is that when you looked at the photo or the cartoon of Einstein here, he had gray hair, just like me here. So the public image around the 1930s, 40s, 50s, after he actually had to leave Germany because of the Nazis, is the one on the right. The guy with the gray hair, with or without the beard, and looking old. In fact, that wasn't the time when he made his big breakthroughs. In fact, unfortunately, he questioned many things he did there at that time, and he didn't get it very far. The time when he made the big breakthroughs was when he looked like this, or this, or this. That was in 1905, for instance, is the famous Annus Mirabilis, the miracle year, where he wrote most of his famous papers. While he was employed, he was looking for a job, and it wasn't easy to find it, so he was employed at the Swiss Patent Office at the time, and he did that on the side there. And the time when you have a scientific originality and innovation is when you're young or younger in that case. So 1905, he was, let me work it out, 26. That was sort of in between those photos there. That's when you're productive. So you guys from the young group, you're the guys where the future lies. We're the guys who have the future behind them and who can sort of give directions where it could go. But these are the guys who lead the development. And in fact, when I look at, say, the development of the COVID vaccines to various people there who are involved, it's mostly people in their 20s and 30s who made the big development even now. So the future lies in your hand, and the time of scientific originality and innovation, in this case it was mainly 1905, was when he looked like this, not like this. And he looked, in fact, I just wanted to say this, he met another student as an undergraduate, a lady, the only lady in his course, Milena, a Serbian, and they got married in 1921, I believe. And this is the two of them in the 1950s in America, or 40s in America. So the relationship lasted. Generally, I know many physicists who have long-lasting relationships, as an aside. One thing, if you want to study this, I want to say is that there is essentially an almost global agreement how these courses are taught, and they're based on these basic theories which I introduced to you earlier on. So the courses are global, and what that means is that you can actually take packages and move around the place. And what I always found most exciting of this is the experimental project. Almost every course has an experimental project. So in our own case, I will now mainly use examples from our own Trinity College Dublin physics course there. Our final year projects devote one semester, or almost a complete semester, to original research projects with either groups in the department or else go abroad under some scheme or the other. And abroad means, there's European schemes. This is my hometown. I had, of course, a good link with my home university. This is a beautiful town, a medieval town called Regensburg on the river Danube here, with a medieval bridge and a medieval cathedral. But some of our students end up in Paris, in I think this is Copenhagen, Berlin, North Carolina, and I can't figure out where this is. But we also have students, and let's hope that we can travel again this year. They couldn't travel, unfortunately, but our students always end up also in China, in Shanghai, for instance, in Sendai in Japan, they were in Canberra in Australia. I'm just trying to remember where we had people. Wollongong in Australia, for instance. The astrophysicists always go to Hawaii for their observations, and also to the Canary Islands, where there's an observatory there. So a big aspect to doing any of those courses is that the courses are global. So the components are interchangeable. And you can, in fact, take something and most people will accept it elsewhere, which is not the case in many other courses. Now, let me just think or look at the job situation. This is basically sort of around, and I I believe you can actually look at the recording of this, so I won't start reading all this, but I have mentioned many of the angles there as well. You can work in the lab as an experimentalist. You can teach either in secondary school, very, very important careers in secondary school. You can, for instance, work in fiber optics, which is very important technologically. Otherwise, we couldn't do this type of performance if we didn't have a transatlantic fiber optic cable connection there. And you can do, for instance, work as a medical physicist in a hospital. And here's an example for one of the MRI scans as a cartoon there. So going through this, you basically, here's the medical physics, meteorology, climate change is important, alternative energy, also greenhouse gases and things is important, computing, electronics and computing programming. Physicists learn automatically how to program, so they're good at programming, and many of our astrophysicists end up doing a lot of sort of aerospace related programming programs, material science, how to make things better and how to make them possible. Industry in general, that can be from chemical and electronic industry, food industry, petroleum industry, semiconductor industry, aerospace there. Scientific civil service is important. An important aspect to this is, of course, there's also a defense aspect there, and some of the American defense labs are world leading in some of their areas. They have the best people there to do this type of research there. You can think about what you want, but it's an important angle to protect and make sure that your population and the world population is safe. So there is also a big angle to that. You don't necessarily have to make bombs like they did with the nuclear bombs there. There's also standards which are very important to keep there. And then communications, I mentioned the telecom, environmental physics, that's basically related again to sort of global warming and so on. Education, very important. Geophysics, how natural resources, and engineering in general. So there's a whole range of topics. And when I look frequently at job ads, they say they want an engineer, and then underneath it says, or any related science. And physics is a related science in that case. Okay, here's a computational Einstein here, there. So I just want to, I only have the Irish connection here, so this is global issue. What do physicists, when they get their first job, they go from airlines, banks, because one thing you do in physics is learn mathematics and logical skills and solving complex problems. Banks like that, biomedical devices, telecoms, electronic devices, teaching, international school, NASA, of course, research and development in aerospace, and hospitals for medical devices. There, you look at this and you find basically every sector can have somebody who has a mathematical and logical analysis skills, and what you get is, in fact, the fact that you can analyze complex projects very, very clearly and focused, and if at all possible, with a mathematic logic way there. And that's important for all. So as I mentioned in my title, if you do a degree of physics, what can you do? I've shown you what you can do, but what next could you do is you could, for instance, also as an alternative, become a rock star. Brian May of Queen has a degree in physics and was doing research as an astronomer before Queen became a success. One of our own guys is a guy called Quivin O'Reilly, who is a fiddler, traditional Irish music. You can become a comedian, and most of you will know Dara O'Brien. He has a degree in mathematical physics. You can become this lady who is no longer looking as young as she did when I got the photo, who is the Chancellor of Germany. And she was, in fact, doing quantum mechanics research in the Academy of Sciences of the German Democratic Republic, which used to be what East Germany used to be called there. And in the 1980s, as a young lecturer, I visited and in fact shook her paws. I haven't washed my hands since, of course, as you know. You can also, hidden underneath here, become, for instance, the head of a university. Our former provost is a laser physicist. The current president of the Dublin City University is a physicist. I think it's the secretary of the Royal Society is a physicist. So your career choices are not limited to just doing science. Anything where you can do logic and critical thinking, like analysis of complex problems, analysis of complex problems in society. These two guys, of course, have different approaches to them, but they have the same problem to do in that case. And or you can start, actually, I should say, I don't have the photos there. You could start a business, and there's many million and billionaires there. For instance, in the 1960s, a guy called Robert Moog invented the music synthesizers. Robert Noyce was a co-founder of Intel, a physicist. Akio Morita founded Sony. The list is long. So your way into whatever you want to do is open there. So I just want to, and this should actually work there, end almost with an old joke. A physicist was asked to figure out how to increase the milk production of cow. The farmers failed to solve the problem, but the physicist had no trouble at all. And he started saying, consider a spherical cow. Now this guy goes normally spherical there. And then the problem was that he could solve the problem optimizing. Basically, this is an issue of surface versus volume there, and the maximum surface for minimum volume is a sphere in that case. And he could solve this, but the problem is he could only solve it with a spherical cow in a vacuum, and no cow lives in a vacuum. So there has to be computational approaches rather than just theoretical approaches to do this. So why would you do physics? First of all, and top of all, I hope I've got across to you, is because it is, you like it and it's fun. And you can see that our students, our 4 astrophysics students a few years ago on the Vomit Comet, it's called. It's the airplane which goes into a parabolic flight. And when you're on the top of the parabola, you have something like 10 or 20 seconds of weightlessness. And here is one of the lads who is weightless for that short period. But you can imagine if you go up at an angle and down at an angle. You understand, of course, why it's called the vomit comet. But it's fun, and they really enjoy do this. So you have the best reason in the world because you like it and it's fun. And what I'd hope to actually also get across to you is that you get a lot of job satisfaction out because you have a lot of options where you can actually fulfill your own career dreams and wishes, and that makes you a happier person in the end. And maybe it makes you also happier if you can actually live comfortably. And I can tell you, you can live comfortably as a physicist. A recent UK report shows that physics graduates earn 30% more than those with no degree, and 12% more than those with degrees in other areas. And other areas which are hard to get in are psychology, biological sciences, arts, and business, of course, there. So people, you do make a good living in an interesting, fantastic field. And I hope I've given you a little bit of a taste how exciting this is, and what nice careers you could possibly consider and where you could go with this. So with that, I stop now sharing and hand over back to NASA.
Yes, thank you very much, Werner, for an excellent presentation. I did ask people if they have got any questions, and we have a number of questions that people have typed. I will go through some of these questions, and maybe Professor Ahmed, who joined us as well, who can come in and read some of them. There's a question here, Werner. There's a general opinion that physics is a very hard subject, and also it's known that there's a shortage of physicists in the world. Yeah, why do you think that is? And how can youngsters, especially girls, how can they be encouraged to study this subject, knowing its branches go in almost every field?
Okay, there's a good few questions here. Now, yeah, I mean, every subject you study is hard because you got to work on it. And the issue, of course, is that you, at some stage in physics, you need some kind of mathematical skills. And that you need to work on the mathematics. And maths can be very hard, as you all know. There's only very few people who have it automatically. So you have to do a work on that. But everybody in every subject will have to do work. And it's not all about maths in that case. And now, in terms of gender balance and equality, yes, physics used to be a very, very strongly male-dominated subject. Now, what we found and find now is that that difference doesn't really exist in a large way anymore. In my own research group, for instance, when looking at taking on PhD students and other graduate students, master students, and I just see two faces here. Hello. Then there was never a gender issue at all. It just, once you take the best students, the gender balance comes automatically. There is, of course, in academia, an issue that there is much fewer professors who are female than male professors. That's partly a historical backlog, really, in my opinion. That'll balance itself out. And a lot of the top class physicists I've seen are actually also from both genders. So there's no gender balance in that case or any other bias in the end there anymore. This used to be, and of course such traditions linger on, but not really. And okay, I think that's basically all I want to say.
Okay.
Now.
Thank you very much, Werner. Physics is a fascinating subject. Why is it difficult for universities to attract students to do degree or a PhD in physics?
I really don't understand this because we never had any problems. So in a sense, this is difficult because no, I think we have a quota and we always fill our quota, and I think the key on to that lies one further back in the school. It's because a lot of people, a lot of teachers who teach physics are not qualified physics teachers, and therefore they don't really give both the excitement and the deep insight into this, and and they some of them focus too strongly on just doing calculations and memorizing things. I think the key is that governments need to, and that's happening now with all these STEM initiatives, need to support all this and change the attitudes of the society. And once that's done, there's no problem. The other issue is, of course, you need to also, and some universities may not do this too effectively, go out with things like open days and transmit that excitement to students in schools and to the general public. So outreach activities are like this one we're doing here now are absolutely fundamentally important.
Okay, well, we have a question from a youngster here. What is an astronomer? Because I want to be one when I'm older. So maybe what's involved in the astronomy of being an astronomer?
Well, let me just actually turn this a bit up. Okay. Well, I mean, we have, for instance, a degree called Physics and Astrophysics. And astronomy is a slightly different degree, which some other universities have. But in a sense, what you do is you study essentially the basics of the universe and of the planets, and there's a whole program in astrophysics. And as an astronomer nowadays, you do a lot of data analysis and big data analysis because lots of the data come, for instance, from satellites, and then they're accessible, and you just actually, with your computational skills, frequently pick out essentially the information which you require out of this enormous set of data. So big data is a big issue for astronomers. The times, I think, when you sat at the telescope looking out are rather limited. Telescopes, radio telescope, you have actually multi-messenger astronomy, which means you don't just use optics, you use X-rays, you use microwaves, you use infrared radiation, you use all sorts of particles. Like neutrino astronomy is a very important, very complicated, but very interesting subject, because neutrinos penetrate the sun, so you can actually look with this or understand things about what goes on inside the sun, where you couldn't see anything else. So it's basically also a bit related with space and space travel around that as well. And a lot of astrophysicists are very excited about going to Moon and Mars.
Yeah. Another question from a youngster. I'm not so good at maths. Can I still get a good physics degree? We're saying that you need to be good at maths.
Yeah, it helps. It helps. But the main thing about good or not good at maths is that you have to just start working on it. And the maths which you do in school is fundamentally different to the maths which you do in university. So what you do when you start your university degree is you start with a couple of maths courses as well as physics and chemistry courses there, and you start literally from the beginning. And you will know within a couple of months if you can manage that. But the key with maths is that you have to work on it. And that's what, when I tried to start studying, I thought I'd study physics and maths and music at the same time. The first thing I gave up is maths. And the reason is because you actually have to invest as much time in studying that as you had to do for the other two subjects. And it didn't come automatically. So the main thing about this is don't believe that you're not that good. If you're working hard on it and it leads to something. And the maths which you do for physics is much more focused on specific methods and specific angles than the maths you do in general mathematics.
Okay, so if we do have any other further questions, you can please do type them in. I'll ask another question here. There is, okay, if you could go back in time, would you once again choose to study physics, or would you rather do something like a computer-based degree, or would you do it all over again?
Well, I should say at the beginning, when I was young, of course, electronics was the big thing. And transistors had just been invented and made available. So I was very excited about electronics and microelectronics. However, for family reasons, the next I couldn't do that because the next microelectronics degree was in the Technical University in Munich, and that would have meant to move to Munich, and the costs associated with it were prohibitive from my family point of view. So I've ended up in the university of my hometown because, of course, living then was essentially free. Living expenses were free, and fees at the time, that's also an important factor. Fees were free. For me, it's very important that everybody should get free access to free education everywhere. That's a fundamental right, and it's not a commercial angle, in my opinion, to make a profit out of education. Education should be accessible to anybody who is in, and I probably would not have ended up in academia. It was never my plan anyway, but would have probably have taken over the little decorating business which my father had at the time. And so the answer really is yes. I enjoyed it, and I would definitely go again. Full stop.
Okay, so when about 10 years ago, in 2010, the Nobel Prize in Physics went to the two Nobel laureates in University of Manchester in the UK for their groundbreaking experiments in relating graphene. There's a lot of youngsters who are watching this and who will watch these, those who have missed it on the YouTube channel. They will want to. Could you, in a nutshell, try to sort of explain the physics that was involved that led to the to this Nobel Prize?
Well, this is really exciting, isn't it? Because it's the physics of sellotape. It's really interesting, and the key to this is that the guys that shows you the Nobel angle to this. The experiment itself is graphene is a sheet system. So what they said is, you know, if I now take a bit of sellotape and stick it on, I can pull off a sheet. And if I do that often enough, I have to end up with one sheet. That's the experiment, which as a Gedanken experiment, as a concept, I can't remember what the Greek philosopher did. The Greek philosopher who came up with the idea of the atom, indivisible atomos, by taking something apart and bring it down to the original constituent parts, and that's what they did. And what the key was is, first of all, they had now the technology to see it with the electron microscopes and things like that. They also had the understanding that there was a theory out there that this would not be stable, and they had the understanding how this could be done so that these single atomic sheets would be stable. And they had the understanding that this was really something very special as a material, because it's so strong, it's so electrically conducting, it's so flexible. And what we now see, of course, from my own research and that of some of the two ladies who are also on the call here, is that there's a whole family of other sheet systems, and you can treat them all the same. And another interesting aspect to this is, of course, with all these Nobel Prizes, there was always somebody who did it before. And in fact, there was, in fact, somebody using molybdenum sulfide, which is a very similar sheet system with sellotape in the 1960s to do single sheets, but he couldn't see them because he didn't have the tools. So having the tools and understanding what you see is the key to this.
Okay. Yeah, one of the things that we've learned, you know, during this, since we started this COVID era, that's the importance of science. Yeah, because then governments have sort of said that, you know, science will dictate. Yeah, and I know through my friendship with the late Nobel Prize Professor Harold Kroto, in the later part of his life, he was a lot involved with global outreach, where he would go out, visit schools and colleges and that, and try to interest youngsters to take up science, study chemistry and that. Are you involved in similar sort of activities where you go out to schools, colleges and that, and try to interest youngsters to take up science and study science?
Yeah, we have a whole program in terms of, we also have the science gallery, which is a combination between science and arts, and they always address topics of societal interest and bring in the school kids into the science gallery. And we tend to go out and do experiments. And well, I can't find it now so rapidly, but for instance, every summer I visit primary school summer camps, and we do some experiments with liquid nitrogen, you know, sort of break a rose to pieces and freeze something and get people excited. You know, it smokes, and or it makes fog, and blow into it, and you break a rubber tube and whatever else, and you can then explain basically that the world around us is not always the same. So if nitrogen is a gas at room temperature, it doesn't need to be a gas if it goes to minus 250 or whatever centigrade in that case. So yes, of course. And what I personally love to do is to do this with primary school kids. So in the age of sort of 8 or 10, who are really exciting. And I could show you some lovely photos. Okay.
And it's great that, you know, nanotechnology is an amalgamation of, you know, several subjects, you know, chemistry, biology, physics, and that. And obviously, I know that some of, in the past, we've had like some of the universities have closed these chemistry departments, and some of the physics departments have shut down as well. How do you think that physics, the way it's been taught at university, how has that sort of changed, you know, from traditional physics to now with, you know, there's with nanotechnology mixing with biology and things like this? What would you comment on that?
There's always short-sighted decisions taken, which frequently are taken on the basis of commercial arguments. And as I said, you know, education should not be a commercial entity in that case. So the question is physics or theology or Hebrew or you name it, Hindi, is something we should have in a university. University means universitas, universal, all angles covered. If it's arts, if it's humanities, if it's medicine, if it's science, we should have actually an overview, and where, for instance, the interaction between the subjects happens, that's where real exciting results happen. So I think it was just a fundamental mistake to shut some of those down, and some of them have actually been opened again. And just to give you an example, we do, as you know, from a materials analysis point of view, have a method called Raman spectroscopy, where you can analyze chemical compounds without touching them. And in fact, what we did is we used that on our most famous national treasure, which is the Book of Kells. And in fact, in Britain, they used it in the British Library on the Lindisfarne manuscript as well. And they're using it in various manuscripts all around the world. Some of the manuscripts in the Middle East are being analyzed. And you can find out things which the arts guys and the historians want to know by applying physics. So there's no limit to your creativity.
Okay. Now, if you were to advise the youngsters, how important are soft skills such as communication, writing, and public speaking to success as a physicist?
Say again, because you've broken up.
Yeah, sorry. How important are soft skills such as communication, writing, and public speaking to success as a physicist? How important are the soft skills to have them?
Yeah, that comes very, very close to my own heart, because I'm actually giving a course in our third year, which is the one when they really focus on physics, and there's similar courses elsewhere on career planning and communication skills. So there's soft skills have to be learned as well, and that includes teamwork, and they have to write essentially a public blog, and they have to find out where the important information is coming from, and then they have to give a talk. And then there's also career planning, how to basically how to look what you want to do and how you will actually get to where you want to do. There is, in fact, we have a course, and most other universities have at least somewhere a course. For us, it's part of our advanced physics laboratory. It's, I think, 10% of the practical lab, and the practical lab is very, very important. So it's a big mark. So we do that, yes, of course, and we teach people teamwork, which is so important as well, as well as doing programming, which is another very important thing.
Yeah, and in your presentation, in one of your earlier slides, you showed some photos of yourself, and some of them in your younger days, and then you said that you're moving more closer to your sort of retirement. Now, when you eventually do retire, what would you like to be remembered for, scientifically, for you?
Oh, this is, I haven't actually, if I'm very honest, I haven't thought about it. Probably for the bringing together the various subjects, chemistry, physics, polymer science, into some materials type thing where materials type subject which you can actually then apply to many practical things like medical devices or communication systems and so on. Something bringing together various subjects and breaking down these very narrow definitions of subjects into a wider science area. And science, as you mentioned just before, people now speak about science, and science is not just one or the other. It's basically the large heading, and the many angles, many aspects contribute to one problem. You look at the problem, and then you come with the biological, with the medical, with the physical, with the chemical, with the mathematical approach, and try to solve that problem. And many of the problems here are really fundamental, like global warming and the climate crisis. That's where we can and where we have to contribute as scientists in the near future.
Yeah, and Professor Werner BLAU is an international authority in the field, and he's well traveled around the world. He goes and gives lectures different parts of the world, and this is one of the things with academics. If you're a professor, if you're research active, and there's youngsters who are watching who would want to follow in the footsteps of Werner, then there is that opportunity to travel the world as well, and he supervised many students. Who are now probably professors themselves in different parts of the world. And I see even in this Zoom meeting now, there is one of the students of Werner Beta is there. I'm not sure where she is now at the moment. I know she was in Trinity College. So yeah, it's and do we have any other questions from anyone? I think we've gone past our time limit. So I would like to thank you, Professor Werner BLAU. Thank you very much for a very interesting presentation. And I'm sure a lot of the youngster people who watch this webinar will find it very useful. And we will be uploading this onto our YouTube channel for those people who have not been able to join today. So please do pass on the word to others. Once we'll send you the link so you can forward that on. And Werner, thank you very much once again. I hope you have a good weekend and stay safe. And hopefully we look forward to probably meeting you once we come out of this this lockdown, where we came out of the lockdown in the UK, but we're in the tier 3 now. So it's still like another lockdown. So hopefully the vaccine has been developed. We hope we can return back to some sort of normality, probably in Easter time. So we look forward to meeting up in some conference somewhere in the world. Okay, thank you very much. Thank you very much, everyone. Take care. Bye-bye. Good night.
Mm-hmm.